Hello everyone. So welcome to the lecture one in topic 6. So this lecture will be on the circular motion. So let's get started. Okay, so circular motions are very common in nature. Okay, so some of the examples of circular motion could be a Ferris wheel. I'm sure you all know what's a Ferris wheel, right? And the other examples could be planets moving around the sun. So when a planet is moving around the sun, it is taking a circular path. Okay, so the planet is moving around the sun, it's taking a circular path. And also the wheels, the commonly used wheels, right? It could be for a bike, it could be for a car, trucks, anything. Okay, so all of those wheels are constantly moving in a circles. Okay. And the other example is running on a circular track, movement of electrons around the nucleus of an atom. So you see, the circular motions are very common in nature. So it makes sense to study different variables that are associated with the circular motions. Okay, so let's talk about. We'll first write the definitions of circular motions and then talk about different variables that are associated with the circular motions. Okay, in physics, circular motion is basically defined as a movement of an object along the circumference of a circle or rotation along a circular path. Okay, it can be uniform with constant angular rate of rotations or constant speed, or non-uniform with a changing rate of rotations. Now in IB, what we will be basically studying is the uniform circular motion. Okay, we'll mainly be concerned about the uniform circular motion and will not be very interested in the non-uniform circular motion. Okay, so our level of mathematics will not be sufficient to study the non-uniform circular motions. So what does it mean to say angular rate? Okay, so what does it mean to say angular rate? What does it mean to say constant speed? So these are the terms that we are going to define now. Okay. Okay, when we talk about a circular motion, we have to understand what's the angular displacement first. Okay, because when an object is moving in a circle, it does stress some angle relative to the center. Okay, so the measure of that angles covered is the angular displacement. Okay, so if you look at this definition here, so the angle moved around the circle by an object from where its circular motion starts is known as the angular displacement. It can be measured in degrees or in radians. So this is pretty clear. Okay, now if you just take a circular path like this and you assume this as the center, let's say my object is somewhere here. So if this is an object here, so the angle traversed by that object in moving from one point to another point in a circle is basically the angular displacement. So if I want to make angular displacement for this one, it would be something like this. Okay, so let me erase the first one here. So this is basically the angular displacement. Now, this angle can be measured either in degrees or radians. So for those of you who do not know what a radian is, I'm sure you all know what a degree is, but if you don't know what a radian is, we'll discuss a little bit about how radian is defined. So the way how we define a radian is basically like this. So if we have L as the arc length, okay, and R as the radius, and theta as the angle measured, we define theta equals to, excuse me, let me just do it in black here. Theta equals to L over r. If you measure an angle by taking a ratios of two lengths, one length being the length of the arc and the other length being the radius, then the number that we get, we define that number as the radian. Okay. Now, for example, let's look at a typical angle that we could write in the radian. So assume that instead of any arbitrary angle theta here, let us assume that it's like this. Okay, let's say it's a let's extend the line of the radius to form a diameter of a circle like this. So this is also r. Now, you know that then the arc length is basically now the semicircle, right? It's a semicircle here now. And the angle is basically this one now. So this is the angle theta. Now, if everybody knows the formula for the circumference of a circle. So if we try to find what a theta is here, for this case, I can say theta equals to the L is the circumference of a half circle, right? So if circumference is 2 pi r for a full circle, for a half circle, it just becomes pi r. So I can just say this pi times r. So this is basically pi r, the semicircle's length, divided by the radius. So r is just a radius, so I just do this. So now I can cancel this two out to get theta equals to pi. But you also know that if we were to measure this in the degree, we know that that should be equal to 180 degree. So then now you have a relationship between two angles. Okay, one angle that you're measuring in radian, and the other angle you're measuring it in degree. So this then is the conversion rule for theta, for degree and the radian. So this is basically a definition that relates radian with the degrees. So let's look into it more. Okay. Let me just recall a little bit. This is the definition of the radian. Okay, so this is the definition of the radian. That's very, very important. This is, the angle is defined in such a way that you take ratios of the two lengths. And by using the definition, we also found out a rule that connects the radian with the degrees by taking an example of the semicircle. So then now we have the rules. Let's look at the common, what are the other angles that we can relate. Okay. Well, because we are familiar with the degrees, let's try to convert degree to radian, because here we are mainly talking about radians, right? So, for example, I want to know what is 30 degrees, 270 degrees, and maybe 90 degrees, and 360 degrees in radian. So if these are the angles in the degrees, so what is their radian counterpart? Now, we use the definition that relates the radian with the degree. So we know that this is true, right? So we know that this definition is true because we just derived it. Now, using that definition, let's try to find what is 30 degrees in radian. So let me use the rules. So pi radian is basically 180 degrees, right? Because I want a 30 degrees, can I multiply this by 30 on both sides? So if I multiply 30 on both sides, then I know that I will have a 30 here. And also, can I not write this as 30 pi radian equals to, I can write this as 180 times 1 degree times 30. And now if I divide both sides by 180 on both sides, so I can cancel the 180s. So 1 degree into 30 degrees, 30 is just 30 degrees. So now I have a 30 degree on the right side. So whatever number I can simplify on the left side, that becomes my angle in the radian. So 3 times 1, so 3 times 6 is here. So pi over 6 radian is basically 30 degrees here. So all of this I got by using the definition that we derived earlier. Now let's try for one more. And I leave the others for you to do it. I will do 270 right now. Okay. So let me try to do 270 now. I will erase this one here. I'll just leave the definition again. Okay. So this is the definition here. Now I want to do 270s, right? So again, I multiply by 270s on both sides. Okay, so I multiply by 270 on both sides. And also, now I can write 180 degree as 1 degree times 180 into 270. And then I can write here also 270 times pi radian. Now, because I don't need the 180 on the right side, I will divide both sides by 180 here. So I can cancel these two, numerator and denominator, because they're same. So on the left side, then I have 270 degrees, right? Now I can cancel this to basically simplify to, I can write, so 3 pi over 2 radian. So this is the radian of 270 degrees. So this is a measure of angle in radian for 270 degrees. So I leave this an exercise for you to find what is 90 degrees and what is 360. Okay. Now, these are very simple. So let's move on to the next part now. Now let's talk about the angular speed. So angular speed is basically defined as the rate of change of angular displacement with time. Okay. Now, when we talk about the angular speed, we're basically looking at how fast an object changes an angle relative to the center. Okay. Now, if you are looking at a particular circular motion which is covering certain amount of angle at lesser time, then you automatically assume that that object is spinning faster. Okay. So in other words, you can basically think of angular speed as a measure of how fast it is moving in a circle. Okay. So by definition, we know that the angular speed is the angular displacement over time. So it's the time taken for the angular displacement to take place. Okay. So the notation for angular speed is basically omega. So it's omega. Okay, so for angular speed, I can write angular speed as omega equals to angular displacement is theta. Okay, so the angle it covers and the time for the angular displacement to take place. Now, suppose I start my time at t1 and I end my time at t2, then the time interval between these two times taken is just t2 minus t1. And if I assume that time interval as just t, then I can write my definition even simpler by just notation t, where t is the time interval between the 2 points. Now, this is the basic definition of the angular speed. So therefore, omega is just theta over t. Let's try to understand this in a little bit more detail. Now, so let us look at these two situations here, where the first question here let's say the first observation here simply says that when theta equals to pi over 2 radian, time interval is just 1 second, right? So which means in 1 second, the object here, which started from the at this point here, so will basically reach here by 1 second. So when t equals to 1, the angle that it traverses will be pi over 2 radian. So basically, I can say that my omega here is pi over 2 rad per second, right? But for the second case here, if you look at it, you will see that theta equals to 3 pi over 2 when time t equals to 1. So at the same time interval, you see that the object now reaches here. So at this point is pi over 2, yes. And at this point it's pi by 2, sorry, pi. And at this point it is 3 pi over 2. So the object would have reached here in 1 second. So I will say that my omega for this one here is just 3 pi over 2 rad per second. Now, the bigger the number, the faster the circular motion it has. Okay, the more faster it's spinning. So this is something that you have to understand. Okay, so the angle covered here is 3 pi over 2 in 1 second. So omega, or the angular speed here, is basically the measure of how fast it is traveling in a circular motion. Okay, so bigger the number, faster it is spinning or rotating. Okay, so that's it for the angular speed. So before we end this lecture for today, I would like to ask you a question where you could try to find an answer. Okay, so here what I'm basically saying is omega is the angular speed, right? Speed. But does angular velocity make sense? Okay, is it correct to say angular velocity or not? So my question to you is, should we be saying angular speed or angular velocity? If angular velocity is a correct term to use, then what's the direction of that angular velocity? Okay, so you will find the answers pretty interesting. Okay, so I want you all to go through this, searching the something about the angular velocity and coming up with the notion of the directions. So we can talk more about the angular velocities in the class. Okay, we don't really need the directions of the angular velocity here, so that's why. So we'll do that much for today. I'll see you all in the next class. So next class we will be talking about the relationship between the angular velocity and angular speed and the linear velocity, linear speed. Okay, so that's it for today. I'll see you all in the next class. Take care.